In this video, I'm going to talk about the electrolysis of molten ionic compounds. First of all, let's define electrolysis. This is the process of using electricity to drive or force a non-spontaneous redox reaction. Remember that a non-spontaneous reaction is one that cannot occur without some sort of external manipulation. The electricity is the source or the manipulation that is necessary to make this non-spontaneous redox reaction take place. We're going to take a look at this problem, how much voltage is needed for the electrolysis of liquid NaCl. I want to point out here that this is liquid sodium chloride. This is not aqueous sodium chloride dissolved in water. This is solid sodium chloride that has been melted. Let's draw a picture of what this electrolysis setup would look like. So we're going to use a beaker, and this is going to be a beaker that can withstand really high temperatures because it takes quite a bit of heat to liquefy sodium chloride. And in this beaker, we are going to fill it with solid sodium chloride, and then we're going to just apply a ton of heat that is going to liquefy the NaCl. So we're going to have this NaCl. The sodium ions and the potassium ions are going to separate from each other, just like we would expect in a regular solution. So we're going to have sodium ions that are in the liquid state, and we're also going to have chloride ions that are in the liquid state as well. Unlike a galvanic cell, this electrolysis reaction is going to take place all in one beaker. We do need electrodes, an anode and a cathode, for this reaction to take place. So we're going to draw some electrodes in here. And the one thing that's a little bit different about electrolysis is that our electrodes that we're choosing for these cells are just kind of anything that is conductive. So a pretty common electrode for electrolysis would be iron. That's a really good conductive metal. And also another really common electrode for electrolysis is carbon graphite. I'm just going to abbreviate that graph. Works really well. We connect the two electrodes with a wire, just like we normally would do with a galvanic cell, but this wire needs to also be attached to a battery because remember, we have to supply some external electricity. So I'm going to put a B here to represent the battery. This battery just needs to be powerful enough to supply enough voltage down into this cell so that the reaction can take place. The overall reaction that's going to be occurring in this is sodium chloride, NaCl. Again, it's liquefied, and it is going to be converted into sodium metal, which is also going to be liquefied, and chlorine gas, Cl2. And let's balance this equation. So since we have two chlorines on the right, we need two chlorines on the left. That means we need two NaCl's on the left, and then that means we need two Na atoms on the right-hand side. So this is the overall redox reaction that's taking place. So if you were to set this up, like at your home, you would be creating sodium metal and chlorine gas. Watch out for that. That's really poisonous. Let's divide this into some half reactions. So what the half reactions look like. So one of the half reactions is sodium ion, two of them in the liquid state. Remember that the sodium ions are separated. And these sodium ions are picking up two electrons and forming two sodium atoms. So this looks like a reduction reaction. The other half reaction that we have going on here is two chloride ions, also in the liquid state, being converted to Cl2 gas, releasing two electrons. So this looks like it's our oxidation. Oxidation is loss. I'm going to make a note of that under each one. So this is, we said this is our reduction reaction because it's adding electrons and reduction is gain. And remember that the reduction reaction takes place at the cathode, red cat. And then this is our oxidation because the chloride is losing electrons, and this is going to take place at the anode. Why do we need to know the half reactions? Why do we need to classify them as reductions or oxidations, cathodes, anodes? Well, remember, our goal here is to calculate how much voltage is required for this reaction. And to calculate the voltage of an electrolytic cell, we use this same equation that we use for a galvanic cell. E cell is the cathode minus the anode. So we need to know which is which so that we can plug them into this equation correctly. The cathode is the sodium reaction, and that voltage is negative 2.71. And the anode is the chlorine reaction, and that voltage is 1.359. And we would also kind of be able to appropriately, put these two numerical values in the right order, because we know that because this is electrolysis, the voltage has to be negative. So this is 4.069 volts. And that number just simply means that it takes 4.069 volts for this reaction to take place.